At the beginning of the course, I think it's really important to talk about, what the subject is as a whole, what the big picture of this is. So, basic fundamental question, what is linear algebra, right? It's a phrase that you may have heard a bunch, you've seen a bunch if you've taken Math 114 and Math 240. One of the things that I notice that students sometimes don't get is a perspective on what that thing is. It's just sort of a catch-all term for some topics. Okay, so let's talk about what that means. It's a two-word phrase, linear algebra. So you might think, oh, this is just algebra that happens to be linear. Okay, what does that mean? There's two words, linear and algebra. Let's talk about algebra first, right? So what is algebra? And I'm going to take a historical/etymological perspective on this. So it starts with the letters AL, and there's a lot of words in English that start with that AL sound. This tells you that this word is from Arabic. In fact, it owes its existence to another Al-Khwarizmi. There's a statue of him. He was a philosopher, mathematician, scientist, etc. He worked at the House of Wisdom in Baghdad. Around 820, he published a book. What is this book about? Well, it was an applied math book, right? So it was for clerks, accountants, judges, anybody who had to deal with like dividing things up for inheritance or measuring land, keeping accounts if you're a banker, things like that. So this book, the title is really translated a little cheekily as The Complete Guide to Unification and Balancing. Now, that doesn't particularly sound like a math book until you realize that the word unification is what Al-Khwarizmi calls combining like terms. And balancing means adding the same thing to both sides. And if you think about it, that's what you do when you try to solve an equation, right? You've been able to do that since the 6th grade. So this word unification is a translation of Al-Jabr, which is where we get the word algebra. I will say something about Al-Khwarizmi. He was not actually from Iraq originally. He's from Khorasan. That's what this name Al-Khwarizmi means, the dude from Khorasan. Khorasan is this region of Central Asia that's quite large, no longer exists as a political entity, but it did back in the day. You should think of this as what we're studying is what you can get if you allow yourself to combine like terms and add the same thing to both sides. Well, we can do a lot with that, right? We can all solve this for t. It's no problem. This is a linear equation, right? So linear equations can be solved. They are the kind of equation that you can solve always just using these two tools, right? If you're willing to add enough things to both sides and combine terms long enough, you'll get a solution, right? It's no problem. The other thing about the word linear is that linear models can be understood, right? So if I give you a word problem like this, you can solve it basically in your head, right? I would go further. I would say that the way that we understand any change at all is by thinking of it in a linear way. So if I describe my velocity to you in miles per hour, what do you think about that? How do you deal with that number that I give you? You say, oh, that's how many miles he's going to go in 1 hour. That's assuming that my velocity is constant. In other words, assuming that my position is a linear function of time. We have real trouble thinking about any other kind of change. So quadratic change or, heaven forbid, exponential change. People are just bad at dealing with that. We always think in terms of linear things. The other thing that's really good about linear stuff is that computers can do it. So I've said linear algebra here. What I really mean is matrix multiplication. Computers are great at that. That's good, right? I mean, we've solved everything, right? Hey, we can do any science, any engineering we want to, plug it in a computer, hit enter, we're good. Not always, though. Not everything is linear. Here's some data. They're not linear, right? These blue points are not along any given line. So what do? Well, we say, okay, there's a linear model, right? We want to understand nonlinear data, so we sort of pretend it's linear, and we try to use that model to help us out. Let's take a look at that a little bit more closely. Let's take a particular data point, right? This orange point, it's not on the model, right? It is not part of that linear model. We see the world out there. We have our models, on paper or in a computer, and, they're not going to match up. We don't expect them to match up, but we want to sort of draw some kind of correspondence between them anyway, so that if our model predicts something, we know what to go look for out in the real world, and vice versa. If I see something out in the real world, I can sort of understand how it fits into the model. So this idea of going back and forth between actual data and your sort of linear model, that's like the bread and butter of statistics, right? It's also the bread and butter of machine learning. If you try to set up a machine learning device to, say, generate tweets in the style of Donald Trump, that is definitely nonlinear data. While your model is going to be a linear thing, and it just spits stuff out that looks pretty close, but isn't exactly the same as the real thing. So in the linear algebra that you've had coming to this class, you probably did a lot of matrix vector algebra. And some students come into the class and they think that this is a trick for solving systems of linear equations. For example, you take a system of linear equations. Here's one. I want to solve this for x, y, and z. So what do? I convert it to a matrix equation. I've got some matrices and some vectors. Then I go ahead and I label each object. So that I've got A and B as matrices, and then vector boldface x, and then this other vector boldface c. I want to solve for x, and then I just realize that this looks a lot like a linear equation from 6th grade. So I add the right thing to both sides, I factor, so I balance, I unify, and then I multiply on the left by a minus b inverse, and there you go. There's my solution, right? So what powers us to go from this system of three equations to just a single equation and treat it like it's a single equation? We have to be able to multiply a matrix times a vector, right? And what is that? It's just scaling and vector addition. So I've got a matrix, I've got a vector. What does that multiplication mean? It means you take the components of the vector and you use them to scale the columns of the matrix, and then you add them together. So that's all you need to do. You need to know how to scale and how to add. Another way to put this is that's actually all you need. You don't need any more, right? So we've treated these vectors as though they were columns of numbers or columns of variables representing numbers. But the point is, anything you can add and scale, you can solve equations with. So what are things you can add and scale? Well, list of numbers, right? That's what we talked about. You could add and scale matrices of numbers, right? You can multiply matrices times each other. So you could imagine doing the same sort of system where you're trying to solve equations whose variables are matrices. Okay, that's interesting. You can do the same thing with functions, right? So if I write like cosine t plus 3 sine t, I just scaled and added functions. Those are sort of in the mathematical realm. There's other things you can add and scale. For example, audio signals. If I play a trumpet and you play a trombone at the same time, then we've added our audio signals, right? You can scale an audio signal. You can play it twice as loud or 1/3 as soft. You can also do this with images. If I take a projector and I project one image and another projector and project on the same screen, then I've added those two images. Video signals you can do. For example, when you use TikTok, right, and you use the stitch, that's what you're doing, right? You're adding two video signals together. Maybe you're scaling them down or something, but there's addition and scaling going on there. So, you could ask the question, I've got 3 audio signals I know how to produce, and I've got a target audio signal that I want to produce. So what are the weights? Do I want to do half of one and a third of the other and like a full one of the third one and add them together? Will I get the desired signal? That's solving a system whose coefficients are audio signals. That's a useful thing to do. The other kind of thing that you can add and scale that's a really important application are things like web pages. Not necessarily just web pages, but other texts, so books. There's different notions of addition and scaling for these, but if you're Google, right, you care very much about this, right? You want to do things with web pages. So there's lots of things you can add and scale. So these are all things that you can add and scale. And the question is, what do they have in common? Right? I mean, they're clearly different things, right? A list of numbers is different from a video signal. There's 3 major perspectives on linear algebra, and they all have to do with this question of what is a vector. So how do you complete the sentence, a vector blank? If you complete that with saying a vector is a list of numbers, I'll call that the computational perspective. That's what computers do, right? They manipulate lists of numbers. They're very good at it. If you took Math 114 and Math 240, you were very good at this, right? There's sort of the physical interpretation, which is to say that a vector is anything that has magnitude and direction. So you very often hear physicists saying this. We did that a little bit in Math 114, right? You have to think about velocities and accelerations and things like that, right? So those have magnitude and direction. The other perspective is what I'll call the mathematical one, which is just a vector is anything that you can add and scale. And sometimes you might think they're just totally different things, but they're not. They're really 3 different perspectives on the same thing, the same fundamental object in play here. It's called a vector space, and that's what we're going to deal with, right? That's the main object of study of linear algebra, is what's called the vector space. I also want you to keep in mind throughout this whole thing what Al-Khwarizmi tells us, right? He's sort of the inspiration for all this, which is that all of linear algebra really does stem from this problem of solving systems of linear equations, and frequently, when you write a proof of an abstract linear algebra fact, the proof boils down to writing down the correct system of linear equations and saying something about its solution.